Welcome back. This is part 2 of spanning sets. So in our discussion of representing all possible linear combinations of a given set, that would be precisely the definition of a spanning set. We are discussing examples in reference to this set of C4. This is a set that contains 5 column vectors in C4, and we're going to explore a question about membership to the span of this set. So let's address the question. Whether or not the set, the vector v with entries 3, 1, 2, and -1 is an element of the span of S. And so what we're doing is asking if we can find values for scalars alpha 1 through alpha 5, if we can find values such that the linear combination alpha 1 times the first vector plus alpha 2 times the second vector plus alpha 3 times the third vector plus alpha 4 times the fourth vector plus alpha 5 times the fifth vector, if this linear combination is indeed equal to that candidate vector to be on the span of the set. So these questions of membership in the span, as we are discussing here, are equivalent to questions of finding solution sets, because finding values for these scalars are equivalent or analogous to finding the solutions of a linear system of equations where the coefficient matrix has these vectors, the vectors that define the set S as the columns. They are the columns of a matrix of coefficients, and then this other vector here in this case called V, this vector would be the last column in the augmented matrix. So we can form the augmented matrix, row reduce, compute the RREF. So let's take note of something here. So in this case, we have 1, 2, 3, 4, 5 columns in the matrix of coefficients. So in this case, we would say that n equals 5. Okay, and the augmented matrix would have 6 columns, so n plus 5, n plus 1, equals 6. And so we have that n equals 5, and the RREF tells us that we're finding R equals 4. Now the one thing that should stand out right away is that by looking at the RREF, you take a look at this row here, and this row is telling us, is kind of screaming at us, right? So this row implies that you're looking at 0 alpha 1 plus 0 alpha 2 plus 0 alpha 3 plus 0 alpha 4 plus 0 alpha 5 equals 1. And so this equation is telling you that on the left side you have 0 and on the right side you have 1. So this is saying that 0 equals 1, which is a contradiction, and that would tell us that as a linear system, this would be a system that is inconsistent. The solution set of this being understood as a linear system is a solution set that is empty. In other words, it is not possible to find values for the scalars alpha 1 through alpha 5. It's not possible to find values for those scalars such that the linear combination equals the candidate vector, right? So there is no solution, and then this is enough evidence to say that indeed V, that candidate vector, is not a member. So this we write this symbol looks like the letter E there. We say if we write this, then yes to membership. But if we say, we write almost the same symbols, but now we cross it with a slash there, this means no, there is no membership, right? So V is not a member. V does not belong to the span of S. That's what we conclude from standard techniques in computing solution sets of systems of linear equations. So far we have defined the span of a set. We are using the definition of span to draw connections. Expressing a member of the span means that that vector can be expressed as a linear combination of the elements of the members of the set. And then we're immediately trying to draw a parallel with what we know about solution sets, specifically solution sets in vector form, expressing solution sets as linear combinations, perhaps the sum of a fixed vector plus a linear combination. So there is a connection between some of the topics that we have learned, that we're studying thus far. And so since the null space of a matrix is a special case of the solution set of a homogeneous system of equations, then let's talk about the following. So suppose that we find a set of vectors that we're calling S, and suppose that we're referring now to a matrix A, and we would like to have the following connection. We would like to relate the null space of a matrix, which itself is a solution set. We'd like to relate that to the span of the set. So is it possible to find vectors that we call S such that the span of that set is exactly equal to the null space of a matrix? In other words, we're asking if that span of that set is exactly equal to the solution set, right? The solution set of the linear system that has that matrix as a matrix of coefficients, and it has 0 as the vector of constants. So if we find the vector form of the solution set of this homogeneous system, then that means that we're going to have to split that solution set in terms of some vectors, the vectors that are used in the linear combination, which is in the expression for the solution set. And so how many of such vectors will there be? Well, the amount of vectors in expressing the solution set as a linear combination, that has to do with this quantity here, n minus r. Sorry, right? So remember that n describes the number of columns on the coefficient matrix. So in this particular example, we're talking about n equals 5, but more importantly, this is the number of columns or the number of variables on this problem, this linear system, and r would be the number of non-zero rows. Okay, so let's keep that in mind. So for this specific example, we find that here we have n equals 5, and then r equals 3. So we are this is the RREF. Please not to be confused here. So this is the RREF of the matrix A. So as you can see, there is not a column of zeros. You could augment the matrix. You could consider A augmented with a column of zeros, and you could go ahead and compute the RREF of this augmented matrix for the corresponding homogeneous system. But in this case, we are simply working with the matrix of coefficients. So in this case, since this is not the augmented matrix, we collect the indices. The set D contains 1, 2, and 4, right? These are going to be the dependent variables. And importantly, the free variables are, in this case, 3 and 5, right? And precisely the number of free variables, follows from the calculation n minus r, which in this case is 5 minus 3, and that equals 2. So there will be 2 free variables with indices 3 and 5 in this case, and we can represent the solution vector. This is based on the information out of the RREF. We can represent the solution vector as in vector form, right? So this would be, everything is here in terms of x3, and x5, and then we can represent the solution vector as a linear combination of vectors that have x3 and x5, the free variables, as coefficients or as scalars. So in fact, this linear combination is added to a fixed vector that has zeros. Remember, each vector here would have 5 entries, so this vector would have 5 zeros. Okay, but because it's a vector of zeros, then we don't really need to address it. And so now we would say, okay, so this vector that appears multiplying x3 is going to be called z sub 1, and then this other vector is going to be called z sub 2. And so those will be the members of, remember, we're trying to make a connection. Can we find a set S such that that set, not the set, but better the span of the set, can we find a set S such that the span of that set is exactly equal to the null space of the matrix A? So we're trying to find such set for which this equality, as a set equality, is true. And so that is addressed by selecting the vectors on this linear combination, the linear combination that we come up with by expressing the solution in vector form, right? So that's the key. We're trying to express the solution in vector form, and that's what gives rise to these vectors that we're calling Z1 and Z2. So indeed, here S would be the set containing Z1 and Z2, and by defining S in this way, then we find that the span of S is exactly equal to the null space of A. So I wanted to introduce that idea from the point of view of representing the solution set in vector form, but all those as an algorithm or some systemic way of expressing such thing. This is the way of doing that. This is a theorem called spanning sets for null spaces. And there's a lot of symbols here, but you get, the more you read this, we kind of revisit this several times. The more you read, the more you get used to it. So the question is, how can you define these so-called vectors z sub j? Those vectors are going to have entries 1, zeros, and the negative of entries that appear on the RREF. Okay, so this is just telling you where you place the ones, those zeros, right? And they are all in reference to the index set containing indices for free variables, right? But this is giving you a recipe for constructing the set S, which is has the property such that the span of that set is exactly equal to the null space. It's another way of representing the null space of the matrix based entirely on n minus r vectors, and there are n minus r of these z vectors. So there is z1, z2, z3 all the way through z sub n minus r.